Yeah, I'm just playing around at the moment, having a bit of fun. It's not often you can have a bit of fun. Circuit is running really well, actually. The only reason it seems to miss a beat now when I disconnect it really is because the HT voltage drops, but the LEDs are sort of consistent. Because the output is designed, I designed it with a Zener diode, so if the voltage on this cap drops to a certain point, it misses a trigger point, because there's no point pulsing it if it's not going to flip the field around. But with the full 60 volts it keeps going, which is what it's supposed to do. I really could do with a bit more than 60 volts, to be honest with you. Because I worked it out, realised when an AC voltage is converted to DC, you get twice the voltage, don't you? Because of the it always doubles up the voltage. But when you divide, when you create AC from a DC voltage, you actually divide it by 2. So I'm not actually getting enough voltage to flip the coil as much as I want to, really. I mean, it's flipping it, but it's not as strong as I'd like it. So basically, that means that I need 120 volts DC, which I could probably do that, yeah. 120 volts DC, and then it would have it, and I'd get my full 60 volts pulse each half cycle. Well, yeah, 120 volts, yeah, I could start to get electric shocks off that. But yeah, it's not a lot of current, so it's not harm, it won't do any harm, it's not a lot of current, so yeah, well, I'll have to see about, actually if I made 2 boards, if I had 2 of these, and they were synced, because these TL494s can be synced together, so you can actually have them in unison. Or I could simply, these MOSFETs can go up to 250 volts actually, that I've put on there, they can actually handle up to 250 volts, so I've got plenty of leeway for an extra 60 volts in there. Means I'd have to use a much bigger cap though. My voltage tripler won't supply me with that though, so I'd have to do it externally. This thing walks like a robot. There's some magnets in it. Wonder what Alan is today. CPU's pretty busy. Let's clip across the output. Let's see what the output is doing. Okay. Right, this is going to go off the scale. This is the output from both MOSFETs. No, that's very interesting. I'm sending a pulse of 2 milliseconds, yet the MOSFETs are actually engaged for 149 milliseconds. The total period is 298 milliseconds. Maybe I need to drop those 100 nanofarad capacitors back down to 10. Oh, it's my my pull down needs to be on earlier, maybe. That's not really a problem though, I don't think. Unless that's back EMF that's causing it. I've got a bit of ringing on my... That could be creating a bit of noise as well. We're getting 37.4 volts across peak to peak on the MOSFET output. That's actually half. Just a bit over half what's the 60 volts DC in. So that's due to the ringing, I think. So I've probably got about 7.4 volts of ring. Inductive reactance. Something smells hot. Oh God, my coil. My coil is getting toasty. Where's my coil at? My coil is at 61 Celsius right now. Well, that's fine, it's not going to melt the ABS. Those old Nicots are bloody hot. handle it. I'll need custom handle quite high temperatures, so I'm not worried about that. This is a duration test anyway, so I need to find out temperatures and everything. How much noise is on there? Oops, I pulled my power lead off. Oops. Don't want to short anything out. I was going to check the Opto isolator driver to see if there's any noise on there. Shouldn't be. Ooh, God. There's a lot of noise on the Opto drive. That's on the gate. Wow. It's a good blooming thing I've got this isolated. That's on the pull down side. The pull up side is, let's see. Oh my God. Can't see what I'm doing. Huh? Wow. That's noise on the gate. I probably need to sort that out. Unless it's because I've just got the probe on there, because it changed when I connected the probe. It doesn't like the probe being on it. The probe is probably interfering with the gate, so I assume it's a clean signal because the output is clean. Oh, cleanish. Where's my blue? Oh, blue's gone off the scale now. That's strange. Oh, my ground's come off, has it? common ground anyway, so. That's weird, what's happened to my blue channel? I'm probably going to knock my offsets or something. Try it off on it. Actually, I'll do the switch. Has the range changed? What's the range? 5 volt. I'm getting some big spikes on there now for some reason. Oh, did I not? Oh, my times 10. Ah, my times 10, I must have knocked it. Yeah, I'm on times 1. Oops. No wonder it's going funny. Yeah, that's better. Looking times 1 Pro. That is a pain when it does that, it scares you. You think, oh, what have I done, what have I done, what have I done? Yeah, there's a switch on the bloody thing and I knocked it to times 1. I wonder it went all conky on me. Right, that's the output without the load on it. And there's still an inductive pulse on there. That kind of noise is what I wanted to isolate from getting back into the circuit, and I seem to be doing a pretty good job considering. Let's check the opto isolator. Drive apart. Oh yeah, there's a hell of a lot of noise on there. I probably need to put a small inductive filter on these opto-isolate outputs to help reduce that noise. I'm not going to scrap this board though. No, I am not. I'm just going to build another one, but not right now. But I want to build a much more stronger one. Can handle more current and a higher voltage. And at the same time, I need to add some. It needs to be on a much bigger board, so I've got more physical separation between the components, and also more inductive blocks to prevent noise from getting back. And then we can get away with bigger voltages. I can put bigger capacitors on the board. But as I said, this board is a prototype. It's to find out the best way of driving these coils. And yeah, this is the output on the opto isolator, not the input, not the part where we're pulsing the diodes. It's the output of the opto isolator going to the gate of the MOSFETs. So you can see the amount, the pulse switching there is tremendous. We're seeing 38.6 volts pulse drive there. It might be a bit too much, I don't know. I did get a latch up problem earlier. This is the other one. When it gets there. Interestingly, oh yeah, the other one won't be showing much because there's no load on it right now. If I put a load on it, switch the coil on, then we should see a pulse on there. Oh, not though. Very strange. I have a suspicion that the second opto isolator wants to turn you on a bit harder. So this is the actual voltage going into the MOSFET at this point into the gate. Oops, my clip fell off. I'm still grounded anyway. I've got the other clip on ground. So there's I can barely see the trigger pulse on there at all. But we're seeing it on the driver one, the first one, which is Q1. We're actually on the gate of Q1 right now. Q1 is the one that gets the voltage from the supply rail. Q2 is the sinking MOSFET that basically discharges the capacitor back to ground, and we're not seeing much on the gate at all. Which is strange. It must be coming on though. Is it warm? Q2 is slightly warm. Q1 feels cool actually. I think Q2 is slightly warmer than Q1, so Q2 needs turning on a bit harder. Let's check the input on the input side of the opto isolator. Well, the pulse is... I'll take this needle thing off, this clip thing off the end a minute. Right. Opto isolator that we're on IC4 pin 1. We have 11.4 volts on pin 1. Pin 2, we have 11 volts, 10.4 volts on pin 2 of IC4, which is the opto isolator. On IC5, which is what turns the MOSFET off, pin 1, is about 10 volts. On pin 1, 9.80. Pin 2 of IC5, which is pull down, is 11.6. 13.2, 13.6. It's pulsed, so it's difficult to get an accurate voltage reading on it. It's pulse 14. So I should be able to, so it's peaking at 14. That's the maximum. So going back to pin 1 of that chip, then that means if that's, we'll find the maximum for pin 1, we can work out the voltage across it. So 9.80, ten, 10.4, I'm looking for the maximum. 10.2, 10.4 is the maximum on pin 1 so far. So it looks like we've got our maximum voltage across the driver of the opto isolators, which is 4 volts. That's the maximum peak voltage across. So I am driving it quite heavily. In a pulse sense. It's not being driven too heavily though, because it's not getting hot. So pin 1, 10 volt. Still. That's still the maximum. Now let's go to pin 2. It's only got 4 pins. 13.4. If it goes up to peak of 14 again, then I'll know I've got my voltage, which is basically about 4 volts peak across the driver LED. It's a sample rate of these scopes. It's every so many seconds. It might be every 2 seconds. So it's pot luck. Well, I suppose I could measure peak to peak, but I'm not triggering on this output. I'm triggering on the yellow. It's 13. Yeah, well, I've got 14 earlier, so I would say 14 is it's just a fraction under 4 volt, probably. So I'm driving these opto isolators sufficiently. That's the pull down one. IC5 is the pull down one. IC4 is what switches the MOSFET on, and I think that one's driving a bit more. Now on pin 2 of IC4, peak voltage on pin 2 is 10.4 volts. Well, that's because it's going across through a Zener, so it will be higher. It's going to be a lot higher than the ground rail is. That's pin 2. .5, 10.6, 10.8, 10.9, Let's try pin 1. Pin 1 is 11.4. Seven point 7.2. I think we need more voltage on this chip, on this one. The pulses need to be a little bit, probably drop the resistor values a bit on there or something. So IC4 is being supplied on pin 1 by oh yes, I had problems with this earlier. I had a 47 volt Zener connected to the output stage, which goes to the output capacitor, and I changed the Zener. I took the 47 volt Zener out because it wasn't working at all, so it's the same one I'm having problems with, and I replaced the 47 volt Zener with a 3.9 volt Zener, which has made it work, but it's still not working very well. So I think the reason for that is that as soon as the voltage is sent out onto the output stage of the output capacitor, that voltage is immediately is pumped up, right, charges up, and if the capacitor doesn't have a chance to equalize before the pulse ends, there's still a low voltage potential and not enough to trigger the off state. That's why I had to drop that Zener right down to 3.9 volts. I think I'm going to stick a diode in there instead, a blocking diode to keep that capacitor charged longer, that 100 nanofarad capacitor, keep that charged longer so that the opto isolator can take that power from the capacitor to keep it on longer, because what's happening is the power from the capacitor is being discharged back through the Zener diode to the output capacitor, and so it's discharging that capacitor, so it's not maintaining that on state long enough. So another thing I could do is put a diode in series with the Zener to prevent voltage from draining out the capacitor. That should solve the problem. So I basically need a Zener and a diode back to back. I didn't have that problem on the high side, because the high side power supply rail is basically always at 60 volts when it's maintained at 60 volts, so that's always high. But I do have a problem on the mid rail, center rail, because that rail is changing volt potential all the time. It's going high and going low. Because of that, the Zener diode is not able to provide the biasing necessary to keep Q2 turned on long enough. That's basically the problem. And that's why when I click my probe on here, I get nothing but frigging noise. No pulse. I I should have a pulse on that. And my coil is really toasty now, so I'm basically going to turn the juice off for a bit. It wants to cool down. Right, I've turned it off. I just want it to rest because I have some more mods to make. I should have bought some milk earlier because I've nearly run out. It's interesting that this has got just stores that last image. There might be another way of doing this actually. I could take the I don't need to take the voltage from the output. I could simply take the voltage directly from the 60 volt input through that 47 volts Zener like previously. But that would mean cutting tracks and I really don't like doing that. Oh god. Always something else. Let's see. Oh, actually, wait a minute. Huh. Duh. I think I know what I have to do and it's simple. All I have to do is take that Zener out and put a jumper. A jumper wire between C11 and which is capacitor for IC2, so I can literally, because these are all isolated, you see, they're not going to interfere with each other. I'm taking the supply that supplies the opto-isolator of IC2, because when that's off it's not drawing any power anyway, and we use that power to provide the biasing for Q2. That should actually be better. Anyway, I'm going to have a think about that. So I'll bring up my schematic in a minute. My computer's really lagging on me. I'm going to close the scope. So basically, I see my bootstrap circuit. What the problem is I'm taking power from the output stage here and supplying it through the Zener. Now the 47 volt Zener didn't work because I was anticipating that when this transistor, this MOSFET, when this MOSFET pulsed on for 1 millisecond or 2 milliseconds, that this capacitor will be sufficiently charged and that there will be enough voltage through this connection, through this Zener, to charge up this capacitor over here, right? I was counting on it, but I overlooked something. I made a boo-boo because the Zener diodes work like diodes in the other direction. So what was happening was my capacitor was charged up and that power was supposed to be stored there, was going to be used for this connection, for this opto-isolator, to provide regenerative pulse to this MOSFET to turn that MOSFET on. There's just one problem. As soon as this MOSFET turned on, it discharged the power that was in that capacitor through the Zener diode to ground. So effectively what was happening was, as soon as this MOSFET came on, we're talking about maybe nanoseconds or something, this 100 nanofarad capacitor was completely discharged, which meant there was no power left in it to supply power to the opto-isolator to keep the MOSFET turned on. So the MOSFET didn't stay on, and so the MOSFET wouldn't basically turn on. So yeah, I overlooked that. My mistake. Well, we all make mistakes. So what I need to do is remove that connection from there. And simply piggyback this connection here onto this one. So this is also the same potential that actually drives this MOSFET, and this transistor that drives this MOSFET here. So this voltage here is not actually being used when this MOSFET's off. The voltage is still present on here because it's constantly being fed to it by this 60 volt rail over here. So the 60 volt rail keeps that capacitor charged all the time, which is why this one works, because this is never discharged. It's always at 60 volts or 50 volts or whatever. So anyway, all basically you need to do is remove this Zener diode completely, stick a piece of wire in the hole and jump that over to here, and then I have my biasing for Q2. So that's what I'm going to be doing. But yeah, we all make mistakes. Well, you see, I saw this bootstrap circuit online and it showed how to do it with one MOSFET. It didn't show you how to do it with two. I guess they had the same problem as me. And because the opto-isolators are completely isolated, when this opto-isolator is on, this one is actually off. Oh, sorry, this one is on as well, but it's turning this MOSFET off. Right. But this one is driven on by a different circuit. It's driven on by a pull down resistor down here to ground. So when it's not receiving the signal, it's actually pulled down by a resistor to ground. So that's how they turn themselves off, by pull down. And normally, when a pulse arrives, it lifts the pull down up. So this rail here is lifted, so a positive pulse goes up through the 300, which goes through this on opto-isolator, and that actually goes through a different route to another LED, to a Zener diode to ground, which biases that opto-isolator on, but at the same time as it's switching that one on, the pulse is connected to this rail here. It's also counteracting the ground that this opto-isolator would be using to turn it off, so it effectively makes that opto-isolator go off while the pulse is present on this one, you see. So the pulse actually travels backwards through this Zener diode. It travels in the forward direction through the Zener diode to turn this LED that's in the opto-isolator off. But when the pulse has ended, this opto-isolator is no longer receiving biasing to turn it on, right? And this Zener diode conducts across its 5.6 volt voltage drop, pulls that opto-isolator on. The reason for the voltage drop is simply we don't want to overdrive it, you see. So it pulls that one down, which goes through this circuit over here, put that drop resistor to ground. So that's how that's what I did. I worked all this stuff out myself, so it's all pretty new. But except for the bootstrap, that was something I got offline. Well, it's basically, it's just like driving LEDs, really. Oh, stream's gonna end, so I'm gonna stop it and have a break. I'll be back later.